Did you know that scientists today are using high-power lasers to create artificial stars smaller than a speck of dust? Today, we're going to go over how machine learning can help make these miniature man-made suns. Hi everyone, welcome back, or if you're new here, welcome to DigiLab. My name is Sid Cowley. I am a doctor in plasma physics for nuclear fusion, and in this course we're going through an intersection of two really fascinating fields: nuclear fusion and machine learning. In the last episode, we went over a simple but powerful way that machine learning and data science can be used for fusion by predicting the confinement of magnetic fusion devices. In this episode, we're going to start talking about how machine learning can aid simulation and modeling efforts in fusion. And specifically, we're going to look at laser fusion. But this is no ordinary episode, and I'm very lucky today to be joined by a leading expert in the field.
My name is Dr. Robbie Scott. I'm a plasma physicist here at the Central Laser Facility at the Rutherford Appleton Laboratory in Oxfordshire. And I'm also chair of something called the UK Inertial Fusion Consortium.
Now, just as a recap, there are many different methods of confining a plasma so that it can reach the conditions required for fusion. One of these methods is inertial fusion, and a subset of that is laser fusion. And that's exactly what Dr. Scott is an expert in.
For laser inertial fusion, what we want to do is we create these things called implosions. So we start out with a sphere the size of a peppercorn, and then we illuminate it from all different directions with lasers or laser-generated X-rays. The illumination heats up the outer surface, causing it to expand rapidly radially outwards, and that creates an equal and opposite inward reaction which pushes all the fuel inwards, squeezing it so much so that you create density and pressure conditions that exceed those in the center of the sun, and eventually you effectively create a tiny little star the width of a human hair, which then ignites and burns briefly, releasing fusion energy.
But how can machine learning help the development of laser fusion? Well, one really vital way is using machine learning to enhance simulations. In laser fusion, one of the most important simulation tools to model an implosion is what's called radiation hydrodynamics. Now, radiation hydrodynamics, or rad-hydro for short, effectively models what happens when a plasma interacts with really high energy light.
So it's essentially fluid flow type models. Energy is input in the form of laser beams. Radiation transport is modeled, thermal conductivity is modeled, and all the thermonuclear burn physics as well.
Now, radiation hydrodynamics can be a really useful tool to accurately and with high fidelity predict what's going to happen in a laser fusion experiment. But these simulations can be quite expensive to run. So here's where we can use machine learning and make surrogate models of these radiation hydrodynamic simulations. In surrogate modeling, we use machine learning techniques to train a model based on loads of input and output data from simulations to effectively learn what the simulations do without actually knowing about the fundamental physics.
Really quite complex, expensive simulations in terms of the CPU resources. Using machine learning, something like neural nets, you can reduce the sort of compute time from what would be a number of days on quite a few CPUs to a couple of seconds.
One very common way of developing surrogate models is through a neural network. Many of you may have heard of them before. Neural networks are machine learning techniques that mimic the structure of the brain. And neural networks effectively consist of layers of things called nodes, which you can kind of think of as features. So the first layer of a neural network consists of your input features. The last layer consists of your output features, and you can have layers in between called your hidden layers. So in laser fusion modeling, your input layer may consist of things like your input laser energy, and your output layer would consist of things like your fusion yield and your hotspot pressure in the center of the implosion, for example. The value of any given node in a neural network is calculated based on a linear combination of all nodes in the previous layer. So in regular English, this effectively means that we go from inputs to outputs in neural networks by mixing up and combining all the inputs in interesting ways. Exactly how the nodes of a layer are combined is what the neural network learns from training data. Before moving on, I should mention that neural networks are often used interchangeably with deep learning. But there's a distinction here. A neural network is only classified as deep learning if it has a sufficient number of layers, typically more than 3. So hopefully you can see how we can use a neural network to build up a cheap and accurate surrogate model for really complex laser fusion simulations. Now here's where things get a little more interesting. Recently, laser fusion scientists have begun training surrogate models on experimental data.
You can create a machine learned model based on the simulations, but then we know that's wrong, so then you can use the experiments to actually then, ground it in experimental reality.
However, there's a big issue preventing surrogate models being trained on experimental data, and that's the lack of data. Neural networks especially are really data hungry and sometimes need tens of thousands or hundreds of thousands of training data points in order to perform well. And the most advanced laser facilities in the world just don't run frequently enough to produce that kind of data.
Our field is an interesting field in that because we can't fire the lasers very frequently at the moment, we're quite data starved in terms of the number of experimental data points we have. Currently, with something like NIV, limited by all of the sort of ancillary operations that have to go on, but you can fire up to about 3 times a day.
But here's where you can get really clever with the data science and use a technique known as transfer learning. The idea here is that you can think of the layers in a neural network as describing the features of a problem, with the higher level layers of the network describing more general features, and the deeper layers of a network describing and extracting features that are more specialized and complex. With transfer learning, you can train those higher level layers on very available low fidelity data, and then train those last few specialized layers on low sets of high fidelity data. In laser fusion, there's not a lot of experimental data, but there's quite a few simulations hanging around. So in a recent study from the laser fusion facility Omega in the US, they developed surrogate models for laser fusion simulations, trained on simulations at first, and then they used transfer learning and retrained the last few layers of the network on experimental data.
They train neural networks on hundreds of thousands of simulations, create a sort of machine learned model which is a good representation of reality, then use a transfer learning approach using the experimental data to sort of fine-tune the models so that then a better representation of reality.
Now, this figure here shows some really interesting results from that study. Specifically, it shows the prediction error from the surrogate models that they built. That's effectively how accurately the surrogate models can predict important parameters like the fusion yield. And the closer the points are to that dashed horizontal line, the better the surrogate model performs. Now, what we can see from this figure is that the data labeled experiment, which is from the surrogate models that use transfer learning, that they massively outperform the surrogate models just trained on simulations, which are labeled low and high fidelity. So this shows that transfer learning can be a really powerful tool to develop surrogate models for laser fusion. But when you develop a great surrogate model for laser fusion, how are they actually used in the field? Well, one potentially powerful way is to leverage the speed of surrogate models to optimize laser fusion experiments by tweaking parameters such as the shape of the laser pulse loads and loads of times and honing in on the one that gives you your best fusion performance. In fact, this figure here from the same study shows just that. For the surrogate models that they trained, we have predictions of the optimal shape of the laser pulse to get the highest fusion yield on those Omega experiments. Now, this is a really powerful use case because there are actually many little tweaks you can make to laser fusion experiments to really increase the performance. A great example of this is the National Ignition Facility, which broke headlines a few years ago by achieving for the first time more fusion energy out of a laser fusion experiment than was inputted by the laser. But what you may not know is that the National Ignition Facility has been running for more than a decade. And those amazing results are the culmination of many small tweaks made over the years that have led to more than 1,000 times improvement in the performance. And this thousands of times increase in performance was achieved mainly through physics intuition and experimental trial and error. Imagine if we could leverage the power of surrogate modeling to optimize the experiments of the future. But the potential use cases of surrogate modeling doesn't end there. In addition to relying just on surrogate modeling and their predictions, you can actually use surrogate models to incorporate more complex physics into your standard simulations.
After decades of development, there's still aspects of the physics in the simulation code which just isn't included. You use machine learning to train and surrogate models which are then incorporated into the sort of mainline codes on the sort of timescales that you need for the whole implosion. Because if you want to be able to design a next generation facility which you're reasonably confident is going to actually produce the goods and give you substantially more energy out than what you put in, you want to minimize uncertainties in every way possible.
Now, I personally think this is a fantastic use case because when people hear machine learning, they often think about cheap ways to replace conventional methods of building up knowledge or modeling. But this use case here shows that machine learning can be used to enhance our conventional tools, working with them rather than replacing them. Right, well, that's all for this episode of Fusion and Machine Learning. I really hope you enjoyed this exploration with myself and Robbie into laser fusion and how surrogate modeling and transfer learning can help simulation efforts in laser experiments. If you are enjoying this series, please feel free as always to leave a like, comment, or subscribe. Your support really means the world to us. In the next episode, we're going to be looking at one of the hardest and most fascinating phenomena in fusion plasmas, turbulence. I'll see you then.